Right, folks. Welcome in for our first talk of this morning here. Now we've got Andy Gelme here, and he is going to talk about his, I had it all figured out, a potential solution for some of the interesting aspects about machine learning. And for those at the back who can't see, we've got some really interesting fun toys at the front here that you're going to get an opportunity to see in action. So, Andy, please take it away.
Well, good morning. It's fantastic to be here. I'm really pleased to see everyone. My name's Andy. My day job is a machine learning company called Silverpond, and it just turns out my hobby and communities and other things I hang out also tends to be around machine learning and robotics. So, yeah. This talk is about an open source project I've been working on for a while. It's also, we use it at work, so that's my day job as well. And but the things I like to do, in my own time is obviously play with robots. And so up here is a couple of small robot dogs, and the idea is just to use that to really stretch the capabilities of the framework. Hang on, why did that not work? Here we go. So let's start with the acknowledgement of country. We acknowledge that we are meeting on the traditional country of the Kaurna people of the Adelaide Plains and pay respect to the elders past and present. We recognise and respect their cultural heritage, beliefs and relationship with the land. We acknowledge that they are of continuing importance to Kaurna people living today, and we also extend that respect to other Aboriginal language groups and other First Nations. So, well, about the title of the presentation, it said about building awesome machine learning programs, and really all the heavy lifting is done by the amazing work of other researchers and individuals and organisations around the world. So the frameworks, the libraries, tutorials, all the white papers, YouTube, we're just an embarrassment of riches of stuff you can freely access. It's just a matter of wading through the myriad of stuff. It's just keeping up with it's really quite challenging because we're in the process of a paradigm shift where the first number of years it's everyone's jostling for position, trying to win big, and then after that sort of settles down a bit, we'll see a consolidation period, much like what happened with mobile phones. There was 6 or 7 years before the iPhone, and then afterwards there was just Apple and Google, basically. We'll see a similar thing here. But for me, one of the aims is to sort of maximise the amount of knowledge share we can do, and one way of doing that is by capturing what you've learned as software. And also one of the things I like to note is today I'm primarily driven by and talking about building. As Kathy and Justin and others have pointed out, there's also a social implication of what we do. It's happened to scientists, happens to engineers, and so it's worth bearing in mind that we make careful choices about what and how we deploy this technology. So my goal is really just to share some of what I've learned with my colleagues and friends about this shift. And one of the big shifts, especially for the younger people in the audience, will be that society is likely to change fairly dramatically, like it's done with the printing press, electricity, computers, communications, light, and so on. These have all changed society greatly, and it's likely and will do the same. And one of these notions is around, for us in the room at least, is well, how may we be developing software in the future? And I'll talk about that a little bit more later, about how we might collaborate with the machines. And the other question on my mind is what happens once the software we've been developing, in sort of the V1, V2 version of software development, what happens when the machines can use that too? What happens, could this framework be used by the machines that are actually being supported by the framework? So anyway, so I'm going to try and demonstrate some of that today, fingers crossed, share some thoughts about what might be down the road in the next week or two. Not brave enough to predict a month away from now. And also an invitation. Just recently started another community around machine learning and robotics, not surprisingly. And we meet monthly in Melbourne, and if anyone's interested, I'd like to share that. So about 16 years ago, started the Melbourne Hackerspace, and still going strong, fortunately. And that was very much a meet in person sort of idea. This will be to also meet in person because a lot of our meetups are about presentation only, and I'm very keen to meet to build. What happens once you've listened to all those presentations and read the white papers, and so. But also this time around, try and do things online. So using basically GitHub to manage everything, including the community. So that if you're not in Melbourne, you're very welcome to join in, and trying to do this difficult tension between experienced people coming along who want to keep going, racing ahead, and every month newcomers turn up and basically sort of have to start from scratch of each person, so that's a fun thing to try and manage. So if you want to, I'll have this slide at the end if you want to grab the QR codes. But basically, there's two repositories. There's a GitHub repository for the community where the discussions and the messaging and website all occurs, and then there's a repository for the software. So about just under 2 years ago, presented an early version of software at EverythingOpen. It's a distributed system. At that point, I was just showing how we could use WebRTC to take channels of video and audio and get it into machine learning pipelines. It was just using predictive ML, so it was face detection or object detection, stuff like that. Obviously, these days, generative AI and agents are the big buzzwords, and so moved to the times. Anyway, I'm not going to go through that presentation because that's already online, but build upon it. So robots. A lot of data scientists, a lot of people doing ML, typically working in the data center because there's already fabulous opportunities just in the data center to basically, I don't know, be looking at insurance things or the myriad of other things people are doing with machine learning at the moment. Looking, make sure that their documents are accessible and being summarized or become like living documents so you can query and interrogate. But I'm really interested in things in the physical world. And this is, I think, what's really going to stretch the MLAI. If you look at any of the work that NVIDIA are doing, like Dr. Jim Fan, where they're basically getting dogs to balance on yoga balls and things like that. It's really, really extraordinary. And they're building these foundation models that are trying to capture not just embeddings and around large language models, but also the idea that anything can have meaning. Basically picking something up, that you can tokenize and you can embed that action and then train the ML on that. And they're doing things with what are called simulation to real, where they can train completely in simulation and then basically put that model on the robot, and it works fairly well. It's pretty extraordinary. But the main drive for me is what these new applications we can build. So there's a list there, but it basically comes down to helping people who have disabilities or other challenges in their life. And we've now got with ML and robotics, there's amazing capabilities that we can do in terms of navigation, picking things up, just things that we take for granted can be difficult for many people. And I really like to see ML and robotics help people in that situation. And also help this area where there's less worries about are my tokens being stolen or all that sort of stuff. Is at least it's an area of hopefully public good, and it's less confusion about that. In Melbourne, the local ML group, we have a tradition of always starting with a joke, and I sort of asked ChatGPT for further help, and that's at the time that's the best it could come up with. I think it's sort of a bit hilarious how lame it is, but anyway, that's the joke. It was for my previous talk about 2 robot dogs and Ellen walking to the bar. Oops, that's me. Right, so I'm going to try and jump into the demonstration, but I'd like to give some preparation about what we're going to try and demonstrate. So some but not all of this. So this is a graph that represents the processing steps that we want this machine learning and robot application to do. And so you can sort of see 3 horizontal lines going through it. There's a line at the top where we're dealing with text, so I could type something in the command line, like a command or something like that. That would then go to the robot agent, which this large language model then looks about taking that into command and interpreting it. So rather than having to have a fixed set of words like move forwards or sit, I can basically type all sorts of English sentences, and the LM will turn that into just what the robot knows. And at the end will become some more, so it will be some more text about, say, yep, I'm happy to do that, or where's that ball you promised me? The middle line is around images. So images come from this robot has a camera, microphone, speaker, a little Raspberry Pi up in its head, a little screen. It's got some buttons for a simple user interface. In the middle, there's an ESP32, which looks after all the motion control for the 12 servo motors in its legs. So effectively, you consider it as like a little embedded system. Images come from that camera. There's detection, so we do predictive ML, yellow detection of the trees and the blocks, basically an IKEA train set. And that then we overlay that on the image so you can see those detections, and then that goes out to the screen. Along the bottom, which I'm not going to show you today because I just ran out of preparation time, is the audio path. And so there's the microphone. So I'm really sad I can't speak to the robot today, which is always a bit of fun. It also means you could control the demonstration as well if you were keen. Goes through speech, text, speech, and back out. So that's what roughly we're demonstrating. And so if you sort of keep that picture in mind, the software, we have to have a way of representing that graph. And so this is the actual the pipeline definition. And so you can see these, the graph has things like OODA, which stands for observe, orient, decide, and act. You can see there's something about the robot agents where you've got the LLM sort of in the heart of this. There's also, like, you can see image detection and so on. So the one down the bottom which says text read TDY, that's where I sort of can type commands, goes to the robot agents which control the robot and then gets out again. That's actually the first line of this previous diagram. So that's how that represent the graph there. And similarly, you can see there's, I don't know if I can, I won't try and select anything. You can see there's a second line there which is around the image detection line. And so basically, this is what we do: image detection, scene detection, we send it off to the robot agent, and then we then write that image out to the screen. That's the second line, and also the third line is there as I was doing audio. So that sort of captures the graph, and in time it would be nice to have a graphical view of that, so it's a little bit easier to write and visualise. Then, for each of these little blocks, you have little pipeline, they're called pipelines, and there's a definition of those. So basically, it'd be the Python class name saying, hey, just read text from TDY or invoke the LM. You can have parameters, so it can say what the source of the data is. This has a little command line history, that type of thing, the prompt. And then most importantly, you also see the input and output. So this will say we're going to get records of text, and we're going to output that as text. And then so an input might be an image that comes in, and the output might be some text because you're doing image to text and describing what's in that image. So the idea is what we have is a conceptual view of what's going on. We have the graph definition and the individual definitions of the Pythons. Hope that makes some sense. Actually, I thought there was one more. Oh yeah, here we go. It is this one. The last thing I want to describe is what's called the system prompt. So with an LLM, you know that we might say something like hello, or write me a bit of Python, or what's a good cake recipe. That's your prompt. And also what is involved as well as what's called the system prompt. This will usually come from instructions from the vendor, or you can add your own system prompt, which says something like you are a friendly chef who will provide me with simple recipes because I don't know how to cook, and that becomes like overall instructions, so that when you say now, tell me how to make a zuckertorte, and hopefully dumbs it down from my level of understanding. So we've got a system prompt here which tells the LM about how to take the English commands, which may be spoken or written, and turn those into commands that the robot understands. So I like Lisp for a number of reasons, and so this robot understands Lisp, which is really very simple things like I can say action arm lower or action arm raise. That's a real Lisp program, just in case you haven't done Lisp before. So I've said to it, you only output formatted S expressions in Lisp. If it looks like a command, then here's a list of some of the commands the robot knows. If the user input matches a query, then you might be able to say something like call this function, get temperature, and also for anything else, it's probably just give a response. So what's interesting about this is the LM is going to basically take the things I say and turn some of those into commands for the robot, and also can take those as a query to then say back to me as a response. And this is like programming in English. It's really kind of cool, especially for people who don't know how to program in C or assembler. This is the rest of the system prompt. If you don't know what to do, then you should say error. It's often important to tell the LMs that because people talk a lot about hallucination, which is a word I don't really like, because I think it's important that LMs be creative and imaginative. That's one of their powers. Often, unless you want to get something really factual, like please diagnose me for a terrible health condition, you don't want any fantasy there. But it is important to tell LMs, if you don't know, then say so. And the last is a little bit of state information. So there's a little bit of information that dog, like it likes fetching balls, and it's the octopus. That's it. It's his best friend. I know it's sad, but there you are. And so that's enough information for us to go. So I'm going to try and set this up. There's some happy dog picture. That's my dog at home, Astra, who can't be here today. Right, so let's see how we go. Right. So we'll talk a bit more on the left about this. On the left is a little dashboard so we can see what's going on. So if I start with it's a distributed system, and I'm doing it upside down at the front. Everything is discoverable. So hopefully, there we go. So now you see the robot's appeared as a little distributed service, and it's telling us some untruths about its location in space. Right. And so the first thing I want to do is start up the pipeline. So you can see here somewhere there's our graph, which I've described before. Somewhere here there's all our pipelines telling you how much I've completed of this project. And now we'll start the pipeline up. And so fingers crossed that's all started. Oh well, there you go. So it has. So you can see up on the left is the pipeline, and you can see the pipelines automatically discover the robot, and you can see yourselves. So sorry about that. Just in case you're worried about privacy, this is all completely local. There's a router there. my laptop and the robot, all the arms are on this machine. So that's one of the things I want to demonstrate. Is it's all running locally. Nothing's leaving this network. This isn't even connected to the internet. So, yeah, I wasn't thinking about privacy. I was just thinking about the demonstration. So hopefully, what I can do is I should be able to take things like the trees. It's pretty good at detecting trees. It's not going to help me. That's really sad. That's really odd. Oh, there you go. Oak tree. So it's a tree. It also gives you the confidence rating on the right. So yes, that's sort of working. And I should be able to type things in. So just down here is a little command line. So I can basically say things like hello, and it says, and you can see it said here, I'm pleased to meet you. So I can say, tell me about yourself. And there we go. So it said here, you can see it's telling me about yourself. The other thing I should also quickly show you is I'm using a server called Llama to run the large language model. And here it's a Llama 3.2 from Facebook. It's an open weights model. It's about a 2 billion parameter model. So that's really tiny. So things like ChatGPT 3 at least, they're I think around 175 billion parameters. This is like 2 billion. So but yeah, it still does very well. But some of the things I also want to quickly show you is I'll just go. Let's see what's in my directory here. If I go vi./LLM, said messages. Just because it was typing is slow, so I can do things like, what are your interests, and type that in here, and I'll say, yep, I love playing with balls and fetching them. This is why I'm really sad I wasn't able to give you the speech stuff today, because that's much better. I can say things like, now this will be interesting because I know it'll fail on this one. I can say, who's your best friend? Oh no, hang on. Oh, it actually worked. I was expecting that one to fail because the idea is I'd show you a smaller model failing and then I'd show you a larger model succeeding. But that one worked. Let's see what you do here. So what do you do if your muscles are sore? And so it's actually I haven't tested that, but hopefully this is going to work. Now that's sad. That hasn't worked because what that is see, it's a little bit of Lisp. That should have gone to the robot, and the robot should have stretched that point. So that's a bit of demo fail. That's because the other thing I should be able to do is say something like ready to catch the ball, and that should it should raise its arm ready to catch the ball. So that's really sad. It's failed in demonstration. So yeah, but what I'm trying to show there is the idea that I can interact with the robot. Some will come back as responses to me, and some will be commands to the robot, which it didn't move. So embarrassing. The other thing is like if I do something like show me you're happy. It should be doing an action to wag its tail. Oh no, it's done that. Wow, this says again, some of these should fail, but it's everything's succeeding. Oh no, it's great. All right. Yeah, okay, find food. So, okay, this one failed. So see, it said find food, and it said I'm hungry. So what we'll do is we'll stop this, and just do a bit of a quick code edit. // we're going for time. LM/elements. So I've got a couple of ML models here. So if I just go down and change it to be this is a 70 billion model, so it's much larger. And first run this again. It'll also take longer to start up. Hang on. That's weird. There we go. It just took a little while to load the model. So there we go. That's just loaded a 79 gigabyte model into the GPU of this machine. But the main you can also see it's taking a little bit longer to respond. So what happens with these models, if you've got 2 billion parameters, that gives you an indication of how many computations it's going to be doing with all the weights and biases as the images and text move through, so 2 billion. And then when you have a 79 billion size parameter, well, it's just simple maths. It's going to take longer. And here we go. so it's now replied. Now if I now do the find food, hopefully this time, here we go. So this time the instruction to the robot was to sniff, and the robot would have put its nose down and sniffed. Just have to imagine the robot doing the right thing. Thanks. But that just that's a very simple example of how the size and capability of the model can change how well it responds to prompts. So the last thing I want to quickly show, oh hang on, that's the other thing, sorry. That's someone should have mentioned that, no, it's vanished. So the last thing I want to quickly demonstrate is, so the robot's gone, I should be able to go history, let's see if I can show one more thing. Here we go. If I do this, so instead of using the webcam, I'm just going to, instead of using the robot, I'm just going to use the webcam. Oops, if I can type the command correctly. There we go. And so what is that? It's the whole same pipeline, but now it's using the webcam, and I should be able to, I think you'll find the object detection works much better with the webcam. The reason being is I train these, this is part of the machine learning thing, I train these models as a given camera, which is different from what's on the robot, and so the detections don't work as well. But you can see here, oh, hang on, it should, it's just being a day, so, yeah. So the last thing I want to do in terms of demonstration is history grep world. Here we go. The other thing I can do is, so when I'm not using the physical robots, fingers crossed this comes up. Here we go, cool. So this is a 3D graphics engine in physics engine in Python. And what I'm doing here is I've created a world, and you can move around this world, and as you move around the world, the image is going out to the machine learning model. So it's just trying to show the sort of pluggability of the architecture. So and also because it hasn't been trained on objects as well, it thinks that young virtual boy is an octopus sometimes, and that green ball's there we go. So this sort of shows you some of the fun of machine learning. The machines only sort of really will say what they've been trained to detect, and they'll pick up other things. All right, so I hope that's given you a bit of a sense of what these software can do, even with some of the demo file. So let's move on. So 20 minutes. Okay, so what just happened? So we ran a complex graph of components across a couple of machines, and you could scale that up. It's also declarative, so you can make changes without having to change lines of code, even though I did that a couple of times. The components are sort of pluggable and reusable for different applications, and try to make it's consistent. So whether you're dealing with machine learning or low streaming or media, IoT, or even robotics like ROS2, the components are all kind of the same rather than being those frameworks are all quite different. Try to smooth out all the differences. We can have these robots in the field, and they could be doing some local computation as well as being up on the cloud. So you can use up in the internet. You can have your data center doing, like, if you've got hundreds of robots out there doing like search and rescue or something else useful. In the data center, you've got this sort of a view over everything, and the robots can be doing local computation so that if they don't bump into things, or if they lose their net connection, they're not lost and useless. The other thing I didn't really show was it's also, with the dashboard, you can observe everything and change things, so it could change the camera view and stuff with the dashboard without having to stop and run code, and also sort of, using the physics engine to basically allow you to simulate stuff, because we don't all have robots yet. Okay, so now I just want to talk about the machine learning stack. Now we're getting time. Wow, what's time? So everyone talks about LLMs, but LLMs by themselves, whilst they do fabulous pattern match and word generation or image generation and so on, there's a lot they don't do. They're pretty much static, so they don't know anything about the world since they were trained. They don't know what the temperature is in Adelaide today, all those sort of things. They don't know if you're an organisation, if you're own documents, they don't know about those, and they aren't particularly great at reasoning. So what we do is they get wrapped with a number of things. So at the bottom you might have your large language model, or above that you'll have some servers. So I was using a llama, so I can basically serve up different models, and it doesn't matter which one I use, they all look the same. Retrieval augmented generation, if you haven't heard of that, what that means is that you can have your own documents, and you can have them fed to the large language model so you can do queries on those. I'll talk about a bit more in a sec. Obviously, we use LLMs are not chatbots. They basically have a whole of software and web interface wrapped around them, so you can converse with them. Above that, there's of course data validation, because you want to make sure what comes back for the LLM is in the correct form. You don't want broken JSON. Then there's tool calling. That allows you to get access to information outside the world. So you can basically, you might have a function that goes to the Bureau of Met, gets the temperature. So there's a way of having the LLM have access to the outside world for both finding out information and creating actions. And then what's going to be the big topic this year is as agents, where agents allow you to have goals and do reasoning, and you can loop around a few more times to get better answers and stuff like that. So there's just 4 things you can do with a large language model. That's it. You can modify the input on the way into the LLM. So someone might type something, but you may want to change or augment that, like add to the system prompt, so you can change the input. When the output comes out from the LLM, you can also modify that. You can also then, if you're not happy with the answer, you can actually loop that through the LLM a few more times, and that's another technique. And then the other thing you do is fine-tune the LLM, which experts will do to actually train on specific data or domain to get better results. But this is enough of an escape hatch to allow us to do all sorts of interesting things. So I'll just quickly talk about RAG. The problem with LLMs is they only have a short context size. The initial ones only had 2,000 tokens, which is about, say, 1,500 words. That's not much. It's not even a document or maybe a large email. And so how can you get to an LLM to respond to a document if it can't fit it in? So what you do is you break the document. If you attended Kathy's talk yesterday, she saved me all the trouble having to explain tokenizations and embeddings. She did a much better job than I can. But the idea is that you can tokenize your documents. You can get their embeddings, which extracts semantic meaning. You can then use what's called a vector database, which knows how to, because embeddings are just big high-dimensional vectors. And what you do is you can run in input. So I might ask and say, if I'm working in a company where it's like health and safety stuff, I might say, well, how can I do this operation safely? So what does it? Tokenize and embed that question. It compares in the vector data and goes, oh, here's a fragmented document which talks about the health and safety regs, and that goes into the context of the LLM. So you don't have to feed the LLM all of your documents, because, for example, let's take Harry Potter, 7 novels. It's about 1 million words, which is about 1.3 million tokens. That's currently about the size of the biggest context you can get from something like Google Gemini. So great, you can basically slip all of Harry Potter in and ask anything about wizardry type shenanigans and get an answer. But most organisations have way more documents than 7 novels, and so you need RAG to, even on large context models, you still need to be able to use RAG to manage all your documents. So hopefully that made some sense. The other way we can use these techniques is what's called tool calling. So, for example, I'll take the example of trying to find the temperature today. What you can do is, you modify the input to the LLM by saying, hey, here's a whole bunch of functions you've got, like we can get the temperature, we can get at the humidity, we can find if the pizza shop's open, all that sort of information, and it gives those list of functions. And they usually do it in the form of JSON. And what that allows you to do is say, here's the function name, here's its parameters, there might be the location that you want to find a weather in Adelaide, and also a bit of description. That's all the LLM needs. It basically figures out from reading that when it should call the temperature function. So you do that, and you ask your query about, well, hey, here's a nice day to have a picnic. The LLM will respond, and its output will basically be this bit of JSON at the bottom. It says, I need to find the temperature. It'll basically include the get temperature call. You can then call that function, send the result back into the LLM, which will say it's 23 degrees, and you'll get an answer say, hey, it's a great day to go and have a picnic. And so in that case, we're modifying both the input and the output of the LLM, because the LLMs are pretty much just these static pattern recognizing machines. So if you're interested in getting into this, I've just given a quick list of suggestions about over the myriad of choices. From the bottom, what language models you want to use. Light LLM for loading your model. I use a llama. ChromaDB is a good little vector database. I think it sits on top of SQLite. You can use Hugging Chat if you want to make a bit of a chatbot. The instructor using Padanix helps you validate the JSON on the way in and out. And then everyone seems to be using the OpenAI API for tool calling, more or less. They got there first, and everyone sort of copied their API. And then more recently, there's things like for agents. There's Schmoll agents from Hugging Face, or AutoGen from Microsoft, which are fairly decent places to start. Time. Okay. The big thing that's going to happen, people have been working agents for decades and decades, and especially the last couple of years of large language models, and we're going to be drowning in them this year. for sure. So here's a couple of recommendations about Simon Wilson and Chip Hewins. They've written some great articles recently around agents to, I guess, get some signal from the noise. But one of the problems is Simon Wilson did a bit of a poll to find out agent definitions. There was about 200 different responses, so people just aren't agreeing on what agents are at the moment. But for me, I insist that if you're an agent, you must have agency, you should be able to have a goal and state, you should be able to make the two planning and some decision making, maybe have some memory, and that really makes you an agent as opposed to just a function called like get temperature, a software component. There has been a couple of popular frameworks, so like LangChain, LangGraph, and so on, ChatDev, the list goes on. But it's good to read things like chain of thought, which is one of the techniques that is used for reasoning. So if you want to know a bit more about just some of the heart of agents. And what I'm interested in doing is I'm not going to try and write my own framework to agent framework to compete for everyone. So I just want to wrap all the different ones. So as from month to month, there's different choices. I can just basically plug in the best of breed and not have to change my application code. All right, so just to quickly talk a little bit about Aiko Services, which is the framework we're running. Covered this in the presentation a couple of years ago, so I won't repeat that aspect of it, but fundamentally it's aiming to be a distributed system to basically allow you to do low latency media streaming, which is great for obviously robots in the field who have to have LiDAR and video and all stuff coming in and to be able to deal with it quickly, turn around fast. Distributed systems is a pretty hard area of computer science to get right. We'll have a bit of a crack and then discover where the dragons lie in terms of dealing with failure and security, reliability, all that sort of stuff. So there's a couple of pointers there, if you're interested. Since everything up in 2023, lots of improvements. It's basically around the pipelines of pipeline elements. And whilst you may not be interested in using this work or for whatever reason, I think this is generally applicable to if you're doing machine learning applications with robotics or with, say, media for teleconferencing, that you'll have these issues around you need to basically assemble lots of components in this complex graph. You need to handle failure like media stopping or having errors. You want to be able to attach user interfaces to them like a web server that talks to your pipeline or a desktop, or in this case a little robot. So if you and you want to be able to have streams like web sessions. So if you've got like a GPU, you want to have multiple streams come through that GPU. So you can't have one. If you've got a lot of users, you can't have one GPU per user. So you need to be able to multiplex, demultiplex streams. You need to handle things like data source. So like I want to have componentized ways of reading from files or from HTTP or from a database and so on. So these are these schemes for data. And the thing we're working on is better multimedia support, more examples and ML applications. That's sort of some of the things, areas we've been focusing. But I think I noticed that AutoGen from Microsoft, they completely redid their architecture and they had a shopping list of things they've been working on, and it's pretty much the same list as I've been. So things that are important is with these complex systems to make them easier and even for experts. So I think you can have if you've got a couple hundred agents and things going on, that's a lot to deal with. So you want observability, you want to be able to see what's going on. So we've got a tool that's a bit like Top, but for distributed systems. It allows you to see the running services. You can select one and see its state. You can actually change its state, so you can change login levels or thresholds without having to restop your whole system. You can have custom plugins to basically give you a more specific view of a service rather than just the generic one. So have this dashboard. There's a concept of a pipeline. So a pipeline which the data flows through is comprised of pipeline elements. And the things you can do with pipeline are, you can create the pipeline, you can create streams, you can process frames, set parameters, get parameters, all that sort of stuff. Perhaps not too surprising. But what's important for me is that this has got a very, very consistent interface of verbs and nouns. So it's always create, read, update, destroy, or start or stop, no matter what the thing is. So it's this verb and a noun. And the reason for that is not only it makes it easier for humans to remember the interface, but particularly if you're going to start using this as tool calling for LLMs, if it's really consistent, then the machines can also use this same interface. The pipeline is not is the pipelines. The pipelines are an actor, so that means they're a distributed component, and all you have to do is implement one function, which is process frame. So you basically have the process frame, you have your input variables and output variables, and whether you succeed or failed. That's the only method you have to implement. In other cases, you might want to know if the stream is started or stopped, and that's a spelling mistake. That bottom one should be stop stream, not start stream. But they're the main methods, so it's meant to be a fairly easy way to write components and just plug them in with the graph. The data scheme is just pretty much like a URL, so it says, so you can basically say, it doesn't matter if it came from a file or a message over the network or something you typed in, all the different data that's disambiguated from whether it's text or image or video, so you can plug and play. It's not, you don't have to worry about the Cartesian product of all these schemes and data sources and so on. The data sources are things that appear basically at the head or tail of your pipeline. So a data source might be you're reading from a file, say you're getting something from HTTP, and the data target might be, I'm going to write that to the file system or send it off to the robot. And these are specialised pipelines that allow you to get data into and out of these are specialised pipelines that allow you to get data into and out of your pipeline. And so they're a bit like bookends, so you should be able to attach a data target to a data source and link everything together. So the final thing I think I'll talk about in data structures is we can take a data source like an RTSP camera or something like that, or a LiDAR. You can take a data target, which would be to talk to the servo motors and make the robot move. But I think of things like a device like drones or robots are really these collections of data sources and data targets because they have a lot of different types of data coming out of them. So it might be like GPS, it's velocity, all sorts of navigation aids, and also there's a lot of things to control, like it's got its arm and gripper and so on. And there are also things like protocols like WebRTC, which are great because can be difficult to use set up as a server, but they're great because they can combine all this information to a single channel, which is quite convenient. Those devices. So a little bit on functions. Before the ML stuff really came along, first in 2014 with predictive ML, and then in 2022, 23 with generative AI. I was really interested in the functions from a distributed systems perspective. If you can turn a function into data, you can send it across the network, you can store it in a database for later, or once functions become data, it's a very, very powerful technique. It's not just, you call this function now, it happens on the same process, and that's the end of it. So you can do distributed systems, you can do tasks and stuff like that. And and typically, especially in web development, you use JSON to send these messages around. And but I was also interested in being able to send code across the network, because if you can send code across the network, you might find the network slow, but if you can send the code over to the device, you can do all the processing on the device. And it's also handy for reducing network traffic, because you can send a filter. Cool, better speed up. You can send a filter and say, hey, only send these types of messages, and so by sending the code, you can dramatically use your network traffic. And so that's why I started looking at lists, because you can see here, the list expression is fairly simple to read and write, whereas the JSON is a little bit messy, and you certainly don't try and do programming in JSON. So then, once I found out that with tool calling in large language models, you go, oh, awesome, it's all about functions, so it was a nice win. So just quickly talk about the tool calling approach I do is basically to wrap up, basically turn actors into things that are tools. So basically have like actors around your environment. Another actor might know how to do financial transactions or that type of thing, or book a flight. And so the idea is that you can use these different actors dynamically and start solving those rather than just being a big blob of Python. So I think that in these early days now, people are just basically saying, oh, here's a whole bunch of functions, but think about how to differentiate them or manage them or change them, having to restart the whole system. So what next for ML? As I mentioned a few times now, there's going to be a lot of talk about agents, so I won't say much more about that. Hopefully we'll see improvements in the open weight models. So there's some great models which deal with text, so text in and text out, so just like chatbots. We're seeing a few last year which allow you to open models which allow you to take images and produce text, so like scene description, which is fantastic. Take a photo and it's a room full of people. We haven't seen much yet in the streaming speech yet, but I think that'll be next. And what's important about the open weights is for reasons of privacy or maybe you've sort of got an application that's disconnected from the internet, you need to be able to run models locally, which is what I'm doing here today. And it's fantastic what you can do with quite small models. And so as these models become more capable, that'd be good. I think my guess is we'll also see some improvements in reasoning, because as people move more to agents and need these agents to work reliably, we need to be able to reason and plan carefully, and also memory. So there's different types of memory. There's semantic memory, which is what's used in RAG, where we're basically attaching semantic meaning to the memories you have, or the document fragments. Episodal, which is like what we put in a time series database. This happened at a certain time. And procedural, which is like a memory in terms of like how do you cook a meal, for example. It's a set of instructions. So something I think a lot about is what's called theory of mind, which is basically your own self-awareness and for yourself, and then being able to observe others, like we're doing in the room here today, and you go, that looks like a person like me, so I can make some assumptions about that person's beliefs and behaviour, and that can really help with ML in terms of answering questions, because if you understand the intent behind a question, you can obviously you can give a better answer. So I think that's an area to know about. I'll have pretty much our time. Oh, it's one of the experiments I did where I said, you can just practice with a chatbot. You say, oh, you're a robot dog, and you see another robot dog. What do you think? Oh, the dog is running for the. This dog is looking for a charging station. What do you think about that? And so it's basically infer stuff. So running out of time, so I'll start to wrap this up. Pretty much done. 2 minutes. 2 minutes. This is an important one. This is about software version 1, which is us just writing code. Version 2 is using predictive ML. We basically send a lot of data to the machine to basically learn how to detect objects. Version 3 is perhaps what we're doing now. We're basically having, we've used ChatGPT and Canvas to collaborate and write some Python code, that type of thing, but more of that. So I'll try and finish with this bit around programming theory building. So this is from Peter Now, who's a computer science back in the 80s. He wrote this article where he really talked about what programming is you're building an understanding between individuals and a team of developers where you're saying we're understanding what the problem domain is, we're understanding what the solution space is, and a mapping between these two things. And he's saying that's the essence of programming, and perhaps something along those lines is what we might try to build out with these machines and machine agents, so that we are collaborating with and also understanding what's going on, because we don't want to live in a world where we no longer understand the code's been written by a bunch of AI. So it's there. Anyway, so I had a few things about what's next for Aiko Services, which is a lot of agent work, just more better distributed stuff, graphical UI, support for model languages. It's just a big shopping list of stuff, a bigger robot dog. And that's come to the end. It's about the end. So is there time for a question or?
Yep, so we've got time for a couple of questions.
Oh, awesome. Yep. Anyone feeling brave enough? I wish the dog could answer. I feel disappointed. Hey,
do the dogs move?
They do. This is the thing about doing live hardware demonstrations. There's a big risk of embarrassing yourself and looking a bit incompetent. They do move. Actually, what I'll do is I'll put it into a little demo mode. Just so yeah. I know. I like being a bit brave and trying to. I think that's my code. See. This little demo is like doing face recognition and looking at fingers. This is just a silly one which is stuff. Just shows it moving and sings a little song just to see if it does actually move. So is there any other questions whilst the end of the
Hi Andy.
Hey, Andy.
Thanks for that. I just had a question about the server you're running the llama models on. Is like how much specs and cost and things like that are you right for that one?
It's a very expensive MacBook.
Right.
And
where do you see that going in the future, I guess, in terms of what can be done?
Okay, so that's another answer. I've got my actual machine I use a lot is Model like Butter laptop there. That was an X demo for like about $1,500 as a modest gaming GPU unit, like an RTX 3060. And the only limitation on that is it's got 60 rep GPU RAM. Oh yes, every Chinese robot takes a whiz. That's the thing they do. It said this morning, actually, so that's for buttons. Yeah, so back to that. So yeah, you can actually just use like a $2,000 gaming laptop and do quite good work on that. The reason I've got the Mac is it's got 128 gig of memory, so which is why it's spending money, and I can throw a 96 gigabyte model of that, and so I can really do experiment with large language models and all those sort of things. So yeah, you can get by with an average gaming laptop and do quite good work.
And are you going to be around the rest of the day?
Yes,
if anyone wants to catch in and have an in-depth conversation, I want to say thank you very much for this. It was very, very interesting. We have a little gift for you. Display with colour.